Hi guys, in continuation of our lecture on SVM. So today is the second lecture on that. So we have in our last lecture we have seen that for a linear SVM our objective is to find out the margin, basically for the maximum margin, so as like what we can separate the data into the both sides of it, isn't it? So now this when we talk of margin, our objective is to find out the maximum margin. This is also called maximum margin hyperplane. And then until now we were just discussing about for binary classification only, a classification of two classes. So in this context, now in this class we will be covering how to compute the margin. We have seen that maximum margin what is maximum margin hyperplane, that we have seen. Now in this lecture we will see how to compute the maximum margin hyperplane, MMH, and then this computing this maximum margin hyperplane, this can basically be formulated as an optimization problem. So we will see how to formulate this as an optimization problem, and this to solve this optimization problem we use Lagrangian multiplier method, which we will be discussing in this lecture. So now first is the computing margin of maximum margin hyperplane. So in the last lecture we have already learned that the equation of the hyperplane is in the matrix form, that is Wx plus b is equals to 0. This already we have seen, isn't it? So what is W, where W is equals to different W1, W2 depend on how many parameters, X has how many features, how many parameters. So accordingly that we have the different coefficient W1 to Wm. If X has m features, then X is equals to X1 to Xn, and B is a real constant. We have seen that, isn't it? And we have also seen that we have labeled plus as one class and this is the plus class, this is the minus class, and we can predict the class level y for any test data. Given any test data x, we can predict the class level y. This is the way. Y is equals to plus x if Wx plus b is greater than 0. What happens? This is the, if this is the hyperplane, anything which falls in this range above the hyperplane, it is above the hyperplane, it will be Wx plus b, it will be greater than 0, and below the hyperplane, this side it is Wx plus b is less than 0. So we will get a x class plus class if Wx plus b is greater than 0, we will get a minus class if Wx plus b is less than 0. This already we have seen. Now in the equation Wx plus b is equals to 0, what does W represent? W represents the orientation, isn't it? And b represents the intercept. Now this any straight line, if y is equals to mx plus c, what happens? If we just scale up or down by dividing a non-zero constant, what happens? We get the same hyperplane. If we scale it, if we multiply it, or if we divide it by a non-zero constant, we get the same hyperplane. So there can be infinite number of solutions using various scaling factors, all of them geometrically representing the same hyperplane. Okay, if we just scale up by multiplying it by some numbers or by dividing it by some numbers, both W and B will essentially get the same hyperplane. So there can be infinite number of such solutions. Now, so this leads to a confusion. To avoid this confusion, what we do, we can make W and B unique by adding a constraint. So what we do, we want to make this unique, so that if we add a constraint, so this unnecessary confusion will not be there. So what did you do? Basically, in other words, this is a hyperplane, and we draw two parallel lines, which we already have seen in our last lecture, isn't it? So and this helps us also to avoid this confusion of infinite number of hyperplanes. So what we do is that I am just writing it here. So basically Wx plus b is equals to, if I write k, okay, plus minus k, because k plus is above the hyperplane, minus is below the hyperplane. So plus minus k, if I divide it by k both sides, so this I can write it in this form, more generalized form. So Wx dot x plus b dash is equals to plus minus 1. Okay. So now it may be noted that this Wx dot x plus b dash plus minus 1, it represents two hyperplanes parallel to each other, which we have already seen, right? So now this Wx b dash is unnecessarily, it will create confusion. Just for clarity, instead of W dash, this is nothing, just the parameters only, isn't it? So instead of that, we can just write Wx plus b is equals to plus minus 1, just two parallel lines on the both the side of the hyperplane. Okay. Now we got this. Now having this understanding, now we are in a position to calculate the margin of the hyperplane. Our objective is to find out the maximum hyperplane, the hyperplane which will have a maximum distance, right? So now we are in a position to calculate the margin. So how we will calculate? So here we have we will see two different methods. First method, say suppose x1 and x2 are the 2 points on the distant boundaries. Since these are the two distant boundaries, say this is B1, say this is B2, or whatever it is, or the reverse. So x1 and x2 are the 2 points on the distant boundaries B1 and B2 respectively. Thus what happens? I can write wx1 plus b is equals to, if it is in this boundary, so I can write this, and if it is in this boundary, then I can write wx2 plus b is equals to -1, or if I take both together, I'll get this, isn't it? W dot x1 minus x2 is equals to 2. In fact, if you see here in this figure, see this is one vector, this x2, x1, what are these are vectors, isn't it? This x2 is one vector, this is one vector. Okay. So now then what is this? This is nothing but x1 minus x2 vector, isn't it? So if I want to find out the magnitude of these vectors, how will I write? So d is nothing but the this vector x1 minus, here what I have written d is nothing but this vector. So what is the magnitude of this vector? Basically, why I want to find out this? This is basically the distance between two vectors, isn't it? This is because this is one vector, this is one vector, right? And so this is the distance. Let me rub it and show it again. So this is one vector, this is another one vector. So this will basically give the distance between these two vectors. Okay. So now distance between these two vectors, if I write it d, I'll get this. I can write it in this way, because this is nothing but a dot product. W dot x1 minus it is nothing but a dot product. When we write the since this is a dot product, if I take the magnitude of these vectors, can I not write it in this way? Is equals to 2 by what is this, and what is this equals to this. When I want to find out the magnitude of W, it is nothing but square root of W1 square plus W square plus up to Wm square. It is in a m dimensional space. Since we are considering x as m attributes, so W will be also in a m dimensional space. So the magnitude of W will be this. So what we got, this distance between two vectors is 2 by magnitude of W. Okay. This is one method of calculating the margin. Let us see the second method of calculating the margin. Second method of calculating the margin. So now see, consider the two parallel hyperplane, say this and this. It is the same hyperplane what we have usually considered, initially what we have considered. Let me write it here, W1 x1 plus W2 x2 plus b is equals to 1 and another one is W1 x1 plus W2 x2 plus b is equals to -1. Isn't it? It is a plus -1. So if I take b this side, what will happen? So it will be W1 x1 plus W2 x2 is equals to 1 minus b, and similarly this I will get a -1 minus b. So 1 minus b if I write b1 and -1 minus b if I write b2. Okay, if I write b1 and this I write b2, then this equation I can write it in this format. So do not get confused why suddenly I got b1 and b2. This is nothing. b1 is 1 minus b, b2 is -1 minus b. Okay. So these are the two hyperplanes. Now these are the two hyperplanes, because we have already seen. Now if this is so how distance between, we want to find out the maximum distance between these two hyperplanes. So max distance between these two hyperplanes is this distance, isn't it? This d. So how do I find d? So this d is nothing but this AC, this AC. So if somehow I can find out the value of AC, that AC is nothing but d. So how will we will use some simple simplification to find out the value of AC. Now from these two lines, H1 and H2, whichever line, whichever hyperplane you consider. So what will be the slope? Slope is nothing but the minus W1 by W2. From this line you can find out the slope, right? So what is the slope? Slope is nothing but tan theta, and what is that? This is equal to minus W1 by W2. Okay. So now here if you see what is this this angle is theta, then what will be this angle? This angle will be 180 minus theta. So now if I find out the sine of this angle, and now this is what? This is the hypotenuse, this is the perpendicular, this is the base, isn't it? So in triangle ABC, AB is the hypotenuse, AC is the perpendicular, and the distance between this H1 and H2. This AC is the distance between H1 and H2. So now if I try to find out the sine of this angle, what is this? 180 minus theta. 180 minus theta is nothing but this AC by AB, perpendicular by hypotenuse sine theta. So what we got? This is one expression we got. So here AC is equals to AB dot sine theta. So if somehow if I can find out this value of sine theta and value of AB, then I am done. I got the value of AC, right? So now here, how do I find out the value of AB? AB is easy to find out. What is the distance from here? This whole distance minus this distance, isn't it? This is AB, this is from 0 to B. If this distance minus this distance will give me AB distance. So this is how I got AB, and I know tan theta is also minus W1 by W2. If I know tan theta, I can easily find out what is sin theta. Sin theta, I found out this. Simple calculation, right? So I found AB, I found sin theta, so I found AC. So this is my AC. AC is equals to magnitude of B2 minus B1 by root over W1 square plus W2 square. So what is B2 minus B1? What is my B2? B2 is minus 1 minus B, B1 is 1 minus B. If I see, so my this is basically B2 minus B1 is nothing but, this is nothing but actually 2 by, isn't it? This is nothing but that we got the same thing. Here also we got, the first method also we got the distance between the two back to hyperplane. Here also we got this, and using this next method also, this is what I got. In SBM literature, this margin is famously written as mu of WB. This margin, this is called mu of WB. So this is my margin now. So now I know this is the margin. Now what is that actually? Basically we will have to find out that, finding the maximum margin hyperplane. So the training phase of SBM involves estimating the parameters W and B for a hyperplane from a given training data. So what is the hyperplane? Our hyperplane is Wx plus B is equals to 1, isn't it? So plus minus 1. So now basically our hyperplane is Wx plus B is equals to 0. The Wx plus B plus minus 1 is the parallel lines which is parallel to the hyperplane in equal distance. So now our what we need to find out essentially in all the analysis what we have done, regression analysis and classification and whatever, we just need to find out the parameters. Here what is the parameters? The W and B is the parameters. So now we have to choose the parameters in such a way that the following two inequalities are satisfied. These are the two inequalities, right? One is W dot xi plus b is greater or equals to 1 and W dot xi plus b less equals to minus 1. If this is for the plus class and this is for the minus class. Mind it, I am again mentioning we are doing for binary classification. So one is below the hyperplane. So below the hyperplane it should be minus 1, above the hyperplane it should be plus. So we have to choose the parameter in such a way so that these inequalities are satisfied. Okay. So this condition imposes the requirement that all the training tuples from class y is equals to plus must be located on or above the hyperplane Wx plus b is equals to 1. Okay. All the tuples belonging to this class, where it will be located? On or above. It will be located on this line or above. Similarly, any tuples belonging to this class will be located in this hyperplane or below. Okay. So now, these are the two inequalities which you already seen. If these two inequalities, if we summarize together, so these two inequalities we can write it in this form by combining these two together, isn't it? Can't we not write it? You see, this is if Wi is equals to 1, for some simplification we are writing, it is plus and minus, basically plus class and minus class. So I am writing W1 is equals to 1, another one is Wi is equals to minus 1. There is nothing but the one is above the hyperplane class and below the hyperplane class. So if this is the case, if I put these two together, I can, this is my inequality now, joining these two together. So, Wi, this is my inequality now. Fine. Note that any tuples that lie on the hyperplane H1 and H2 are called as support vectors. That tuples that lie on the hyperplane, those we call it support vectors. This is very important. Like here we see this is one support vector, this is one support vector which lie on the hyperplane, that is called a support vector. Essentially, the support vectors are the most difficult tuples to classify, because why it is most something which is away from the hyperplane, which is much above the hyperplane, definitely it will be in the plus class, I know. Something which is much below the hyperplane, it will be in the minus class, I know. But something which is on the support vector means on the what to say, on this plane, this is most difficult to classify, isn't it? That's the thing. So, because the distance is very less, the support vectors are the most difficult tuples to classify, and they give the most important information regarding the classification. Most important information regarding the classification means, we will see later, the support vector actually it defines the complexity of the SVM, and so that is why we call it, it gives the most information regarding classification, and it has some support vectors also gives, we will gradually see that. Okay. So, in the following we discuss the approach of finding this maximum margin hyperplane and the support vectors. How do we find these support vectors and what are this maximum margin hyperplane? So, now we have seen what is the hyperplane, how we have to estimate. We have seen these are the two techniques. One is the first method. Okay, this is the first method. This is our margin, isn't it? This is our margin. The second method also we got the same thing. This is our margin. This is nothing but the same thing, 2 by magnitude of W, it is the same thing. So, this is the margin. So, now but at the same time it should satisfy the constraint. We have also seen that it should satisfy this constraint, isn't it? It should satisfy this constraint. So, now what we need, we want that our margin should be this margin. What we have seen, our margin is nothing but 2 by magnitude of W, isn't it? That is the margin, and this is the what is then? This is the constraint. This should satisfy. So, now if can't we not put it in as an optimization problem? So, what is the optimization problem? Basically, first we need to maximize the margin. This maximum margin hyperplane means our margin should be as high as possible. We need to maximize this margin. So, now we need to maximize this. If I write it in the opposite way, numerator becomes denominator, denominator if I put it in numerator, then this is equivalent to minimizing the following. This is maximizing, this is maximizing, then I can write as mu dash W of B is equals to, this is if minimizing this, then instead of, if I write it in this pattern, then I need to maximize this value, but I am doing it opposite. So, I am telling I need to minimize this, and under the constraint, subject to constraint this. So, in nutshell, the learning task of SVM can be formulated as the following constraint optimization problem. What is this? Minimize this, subject to this. So, this is how I formulate this as an optimization problem. I need to minimize this, minimize what? W by 2 and subject to yi into W dot xi plus B, and it should be greater or equals to 1, subject to this. Okay. So, now so this is our optimization problem. So, the above constraint, the above stated constraint optimization problem is popularly known as convex optimization problem. This type of optimization problem is also known as convex optimization problem, where the what is the speciality about this? Here the objective function is quadratic in constraint. Here the objective function is quadratic, isn't it? And the constraints are linear in the parameters W and B. So, the specialty is the objective function is quadratic and the constraints are linear. So, this type of things we call it a convex optimization problem, and for convex optimization problem, the well known technique is the Lagrangian multiplier method is used to find out the solution for such optimization problem. So, now we will learn this Lagrangian multiplier method. once we know this Lagrangian multiplier method, then we will use this to find out. Our objective here is to find out the SBM, right? Means SBM means our objective here is to find out the maximum margin hyperplane. Finding out the maximum margin hyperplane, essentially what we need to find out? Essentially we need to find out W, we need to find out B, isn't it? We need to find out the support vectors. Those are the things we need to find out. So for that, we have formulated it as an optimization problem. What is the optimization? Minimize this subject to this. Fine. So Lagrangian multiplier method follows two different steps depending on the type of the constraint. So this what is Lagrangian multiplier method? It has two different techniques. One is we minimize this function. Okay, for us also we have a minimization function subject to, it has a equality condition, subject to gi x is equals to 0, means it has some constraint which is linear constraint and which is equals to 0. That is my constraint here. So I is equals to 1 to p means there can be p constraint, any number of constraint. So another is inequality constraint. Minimize this function subject to this constraint hi x less than equals to 0, and similarly there may be p number of constraint. Okay. So this is equality constraint optimization problem, this is inequality constraint optimization problem. Say inequality constraint, my constraint is equals to 0, and inequality constraint, my constraint is less than equals to 0, and what in both the case we have to minimize the function, right. So our case is also, our case is what? We have to minimize a function, but our case is subject to hi x, if I consider is hi x is greater or equal to 0, isn't it? Sorry, greater or equals to 1. It is an inequality constraint. So now how we do, how we define the Lagrangian multiplier in this way. So this is we introduce a new parameter which we call, it's a dummy parameter, that is lambda. So the Lagrangian of this, how we write it is fx, that is the function, plus all this constraint, summation of lambda I gi, summation of all the constraint multiplied by lambda I. For each constraint we will use one lambda, one dummy variable. If there is one constraint, so lambda 1 g1. If there is two constraint, lambda 1 g1 plus lambda 2 g2. Three constraint, lambda 1 g1 plus lambda 2 g2 plus lambda 3 g3, likewise. So it is summation of all the constraint multiplied by the dummy variable and plus fx. This is my Lagrangian. This is how I write it. Now what I will do is that I will take the first order derivative of this with respect to each parameter of x, each attribute of x. First order derivative of this equation with respect to each attribute of x. So if x has d attributes, so I will be del L by del x1, del L by del x2, del L by del x3, del L by del x4 up to del L by del xd. So this is the first thing, and since we are trying to find out the optimum, so definitely there's whatever we will do the differentiation, first order differentiation will equalize it to 0. So if there are d attributes, so from this del L by del xi total we will be getting how many equations? Total we will be getting d equations. Okay. Next again this will also differentiate it with respect to lambda I. So if there are p lambdas, so we will differentiate all lambda del L with respect to all the lambdas, lambda 1, lambda 2, lambda 3, and similarly we will be getting total p equations. So here how many equations we will get? We will get d plus p equations, and so from this d plus p equations we will be able to find out the value of, and equalizing all to 0, and from this we will be able to find out the values of this all x1 to xd and all the lambda i's. Lambda I, lambda 1, lambda 2 up to lambda p. From this d plus p equations we will be able to get this value. This is the first one, equality constraint optimization problem, how to get the values of the different how to get the what to say, we have to minimize the function. So what is the value of the minimized function? We can know the value of the minimized function. For that we will have to know the value, different parameters of the x. For what parameters of the x we get the minimum value, isn't it? So this gives us the different values of the attributes x which will give us the minimum value. So here is an example also. Suppose we need to minimize this x plus 2y, subject to this constraint, x square plus y square minus 4 is equals to 0. So, Lagrangian how we write? So, see, it was a function of x y and we have used another one dummy, so x y lambda. So, what is this is our function, isn't it, plus lambda into the constraint. Since there is only one constraint, so there is just one lambda. See, isn't it the same thing how we have written fx, how we have written, see, fx, this is how we have written, isn't it, fx plus summation of all the constraint multiplied by lambda I. So, here there is only one constraint, so just one lambda. So, this is what my L. Now, what will I do? I will differentiate this with respect to x, I will differentiate this with respect to y, because there are two attributes x and y. So, first I will differentiate with respect to x, then I will differentiate with respect to y, that is one. Next I will again differentiate this equation with respect to lambda, just there is one lambda, so once. So, differentiating this with respect to s, I got this, with respect to y, I got this, okay. Then with respect to lambda, if I differentiate, I got this. So, I got three equations, how many unknown? 3 unknown, x, y and lambda. So, solving this, I got this values, these are the different x values, y values and lambda values, okay. Now what will I do? So, I got different x value and y value. Now, my thing is that I need to find out for which x value and y value there are different x, y. It is like simple optimization problem. You know optimization problem, you know genetic algorithm, right? How do? We take out the different values of x and y. So, similarly, we got the different values of x and y. Now, which values of x and y actually satisfies our function? We need the value which is minimized, the x plus 2y should be minimized and at the subject to a particular constraint. So, from this we got different values, for x and y, for x, y, lambda we got 2 values. So, from this which value will actually will give us the minimum value, that we have to find out, we will have to solve each and find out. So, total there are how many choice? There are 2 to the power 3 choice, each value has 3, for each variable we got 2 values and there are 3 parameters. So, total there are 2 to the power 3 choice. For lambda is equals to this, we take different x and y values. Definitely lambda will not be used in the equation when we will try to solve, because lambda was a dummy parameter which we have just introduced. So, we will take different x and y values, we try to substitute it, and what we got, if we use first this in this function, we got minus 10 by root 5. Okay. Similarly, if I take lambda is equals to minus and this x and y this values, I got this. Lambda is not necessary, you just take the different values of x and y, okay, different combination of x and y. With the different combination of x and y which gives the minimum, at the same time this also said to be satisfied, x y plus y square minus 4 is equals to 0, this should be satisfied and this should be the minimum value. Okay, here we have seen in this too, you can calculate all the values and see, we have seen has its minimum value at this value. You calculate it and see, we got it for x is equals to minus 2 by root 5 and y is equals to minus 4 by root 5, we got the minimum value. So, now what is the value of x and y? Value of x and y is this is the value of x and y. Essentially, we'll try to solve it you taking different combination of x and y. Take one x, another one y, again keeping that x same, change the y. Okay. Now, again the keep the x constant and change both the x, likewise you will be getting all the combination, put it in the function, see whichever gives us the lowest minimum value, but at the same time whether the constraint is satisfied or not, it is the minimum and the constraint is satisfied, that is my solution. That is for equal constraint. Now, for inequality constraint is a bit complexity is a bit more than the equality. How? It is not difficult. So, the method of solving this problem is quite similar to Lagrangian multiplier method described previously. Here it starts with the same, with the Lagrangian, same, the earlier how we have used Lagrangian, here also we are using the Lagrangian, same thing, nothing till now, nothing is different, but in addition we use some additional constraint which we call KKT constraint. So, this is in Karush-Kuhn-Tucker constraint, in short it is called KKT constraint. So, for inequality constraint, in addition to this Lagrangian, this is we call it Lagrangian. When we introduce the dummy variable lambda, we call it Lagrangian, and in addition to this Lagrangian, we introduce some other constraint. So, what are these constraints? See, one is, first of all, the one constraint is that this Lagrangian we'll have to derive it, we'll have to do first order derivation for each attribute of xi, which we have done for equality constraint. Same wise we'll have to do it for each parameters of xi is equals to 0. And for the equality constraint, we have also done first order derivation with respect to lambda. Here we will not do that. Instead, we have this three constraint. What is? One is lambda I should be greater or equal to 0. That is one constraint. My lambda I value should be greater or equal to 0. It should not be less than 0. My xi value will be less or equal to 0. Okay, xi, that a constraint. My constraint value will be x less or equals to 0, and my lambda I xi should be equals to 0. See, these are the three constraints. Lambda I greater equals to 0. Please remember, when we will solve it, we will be needing this. Lambda I greater equals to 0, hi, that is the constraint, less equals to 0, and lambda I hi will be equal to 0. Okay. Lambda hi is equals to 0 means either lambda I is equals to 0 or hi is equals to 0. Solving the above equation, we can find the optimum value of fx. Now, if we solve this, we can find out the optimum value of fx. So, let us see an example. Suppose we need to minimize this subject to this constraint. Okay. Subjects to this constraint, we need to minimize. So, here in the inequality constraint, our constraint is in less than sign, right. So, less than equals to 0. So, accordingly, we will just do a bit of manipulation and we will bring. So, this will become x plus y minus 2 less than equals to 0, isn't it? And this will become x minus y. From this, we can write x minus y less than equals to 0, isn't it? Just if we bring x this side, the sign gets changed. So, x minus y less than equals to 0. So, these are my two constraints. So, there are two constraints. So, I will be using lambda 1 and lambda 2. So, first is this my function. What is my Lagrangian? Lagrangian is my function, this is my function, plus I have two constraints. So, summation of both the constraint multiplied after multiplication with the dummy parameter. So, this is one, this is the second. So, what is my KKT constraint? KKT constraint is first del L by del x. Here there are two parameters x and y. So, del L by del x, whatever I get, that is equals to 0, then del L by del y equals to 0. So, del L by del x, I got this is equals to 0. First order derivative simple, del L by del y, I got this is equals to 0. So, remember what was my KKT constraint? One is del L by all the attributes of x, del xi. So, here there are two attributes x and y that we have done. And what is the second constraint? Second constraint is my this all by this was my second constraint. I have written it in this. Second constraint is all my lambda 1 lambda 2 is greater equals to 0. Isn't it? Lambda 1 lambda 2 is greater equals to 0, and what is the third constraint? Third constraint is all my hi is less equals to 0, isn't it? What are my constant? Hi less equals to 0. So, this is the I can write it in the x less equals to 0 format also. That means x plus y minus 2 less equals to 0, then x minus y less equals to 0. Okay. So, lambda 1 lambda 2 greater than 0, this less equals to 0, then what is the next constraint? Lambda into hi is equals to 0. So, this is lambda into hi is equals to 0, lambda into hi is equals to 0. This is one constraint, this is one, this is one. So, these are my KKT constraint. So, this many equations I got. Now, with these equations, I got all these equations. So, with this equation, I will be able to find out the value of x, y and lambda 1 and lambda 2. Okay. So, now I will have to find out the minimum value of fxy subject to this constraint, subject to this KKT constraint. All my KKT constraints should be satisfied. Okay. So, based on that, we will have to find out the value. Now, to solve this KKT constraint, we have to check the following test. Okay. So, first, if I take lambda 1 is equals to 0, lambda 2 is equals to 0, what is my lambda 1, what is my constraint? Well, my constraint is, this is the constraint, lambda 1, lambda 2 greater or equal to 0. It cannot be less than 0. So, if I take lambda 1 and lambda 2 equals to 0, if I take lambda 1 and lambda 2 equals to 0, in this equation what happens? Lambda 1 is 0, lambda 2 is equals to 0. Then what happens? I got this is 0, this is 0. So, I get 2 into x minus 1 is equals to 0, I get this expression. Similarly, from this expression I get this 2 into y minus 3 is equals to 0. Okay, from this two equation I get x is equals to 1, y is equals to 3 if I solve it. Simple equation you solve it. So, but however, when I get x is equals to 1, y is equals to 3, what is my constraint? My constraint is x plus y. One of the constraint is x plus y is less than equals to minus 2. This is one of my constraint. Another constraint is y is greater equals to x. The first constraint only, x plus y less than equals to 2, it is not satisfied with this value. X1 is equals to y, x is equals to 1, y is equals to 3. This is not satisfied. So, this is not a feasible solution. Okay. So, if I took lambda 1 is also 0, lambda 2 is equals to 0, the value of x and what I got, that is not a feasible solution. Now, let me take another one combination. So, another one combination, let me take lambda 1 is equals to 0, lambda 2 not equals to 0. Okay. If my lambda 2 is not equals to 0, first look here. If lambda 2 is not equals to 0, you see this equation. If lambda 2 is not equals to 0, then definitely x minus y is equals to 0, isn't it? So, if x minus y is equals to 0, so from this what will I get? X is equals to y, I got to. Another one, if lambda 1 is equals to 0, lambda 2 not equals to 0, putting these values here in these two expression, I got this. This is one equation, this is another equation. Putting value lambda 1 is equals to 0 and lambda 2 is not equals to 0. Lambda 1 is equals to 0, it is gone. So, these are the three equations I got. From this I found out this value, x is equals to 2, y is equals to 2, lambda 2 is equals to minus 2. But what is given? My lambda 1, lambda 2 should be greater equals to 0. So, here I got lambda 2 is equal to minus 2. So, that means it violates my assumption. So, this is also not a feasible solution. So, I took lambda 1 0, lambda 2 0. So, if I see here lambda 1, lambda 2, different combination I can take this 0, both 0, this I got, this is not a feasible solution. Then I take this is 0 and this is not 0. This also I found not a feasible solution. Then I take this is not 0 and this is 0. Okay, I will find out the solution. Another is both not 0. Both lambda 1, lambda 2 not 0. These are a different solution I can get. So, next I took lambda 1 not 0, lambda 2 is equals to 0. Accordingly, I found these are the equations and this value I got. This is lambda 1 is equals to 2, this is also feasible because it is given lambda 1, lambda 2 greater equals to 0 and I got x is equals to 0, y is equals to 2 and it satisfies the constraint also, isn't it? What is my constraint? My constraint is x plus y should be less equals to 2, x plus y less is equals to 2, so it is satisfying the constraint also. This is a feasible solution. And the final solution, what do we find? Lambda 1 is not equals to 0, both lambda 1 and lambda 2 not equals to 0. This what I got. This also if I solve it, I got x is equals to 1, y is equals to 1, but lambda 2 is equals to minus 2. My lambda should be greater equals to 0, that is also one of the constant, KKT constraint. So, this is also not a feasible solution, so just this is the feasible solution. So, what is the feasible solution of this optimization problem? X is equals to 0, y is equals to 2, that is my feasible solution. That is how we find it Lagrangian multiplier, using the Lagrangian multiplier method, how we find out the values of the f x and y, values of the function which will give us the minimum value of the function. So, that we have seen for some example. Now, basically we will be using this method. Definitely our inequality constraint, we will be using the second method, that is the Lagrangian multiplier for inequality constraint. We will be using that method to solve our hyperplane problem. That was our problem, isn't it? For that problem we have we have formulated as the optimization problem. Now, we will be solving this optimization problem using the Lagrangian multiplier which we have just now learned to solve that. Okay. So, now coming to the conclusion, in this lecture we learn about the computation of the margin of the hyperplane, separating the class in the case of linear SVM. We have seen how to compute the margin. We have seen two different methods. So, what is the margin? Margin is 2 by W, isn't it? So, how we have computed, we have seen. Then we formulated the optimization problem to obtain the optimal hyperplane with a maximum margin. To solve the optimization problem, Lagrangian multipliers were used. We got a basic introduction of how the Lagrangian multipliers are utilized. We have seen that. So, in this lecture, we will attempt to solve the optimization problem for linear SVM. Okay. So, with that, I end this class. Thank you guys.